Okay. Yeah, thanks everyone for coming to my talk. I hope you all had a great conference so far. I definitely had. And here's another talk on fuzzing, this time about JavaScript engines. So let's get right to it. Start with some motivation. On this slide, you can see two proof of concepts for fairly common JavaScript engine bugs. It's not really important what the bug here is in particular, so you have the CVE numbers, you can look it up. But this is just to give you an idea what the kind of code is that we are trying to find through fuzzing. And so let's think about how we could write a fuzzer that generates like code, something like this. I guess the question is how do we fuzz JavaScript engines? So I guess the simplest approach to fuzzing is, well, you do dump fuzzing. You just throw random bytes at your target. Yeah, now, as you can maybe imagine, for a JavaScript interpreter, this is not going to be that effective. But I think it's still important to understand exactly what's the problem here. So what's going to happen is that the parser, the thing that consumes JavaScript and converts it to like an internal bytecode thing, it rejects this because it's not valid JavaScript syntax. And so nothing ever gets executed. It stops in the parser. And the parser is maybe interesting for fuzzing, but it's only about 2 or 3% maybe of the engine source code and probably the least interesting ones. So we have to do something better. This brings us to our first requirement, which is all the samples we generate, they have to at least have valid JavaScript syntax. So requirement 1 out of a few. Now, so syntactical correctness, now how can we achieve this? One possible way to do this is with a grammar-based fuzzer. That's also a very common approach. Example here is Domato and many others. The idea is you take the JavaScript syntax, you formulate it as a context-free grammar, and then what your fuzzer does is it takes random production rules. So it decides to produce a expression statement maybe, and then for the expression it decides to use an addition expression and so on. And yeah, so then you could come up with something like this maybe. So this is what a generative grammar-based fuzzer can produce for you. Now the problem here is, in this particular sample here, that it's calling a method on something that's a number, which doesn't work. It's going to throw a runtime exception. And the problem with that is that once the first runtime exception occurs, then the code following that is never going to be executed. So it's not, it's not very helpful. And so the common solution for this is you put everything in try-catch. If you look at some of the common JavaScript or browser fuzzers, you will see pretty much everything is in try-catch. And then it's okay. Every statement executes. If it throws an exception, it's fine. It's getting caught. And then the next code still gets executed. The problem here is if you think back about these samples that we tried to find, at least one of them was a JIT bug. So a bug in a JIT compiler, as we heard yesterday from Bruno. And so for a JIT compiler, these two here are really, really different, right? So there's completely different control flow between the sample on the left side and the one on the right with all the try-catch. So for a JIT, this doesn't really work. And so this brings us to our second requirement, which is that we need a fairly high degree of semantic correctness as well, right? So not only syntactic correctness, also semantic. This is harder, quite a bit. And there are a few options that you can achieve this. One option is you can try to do fairly precise type tracking. Remember this example from the generative fuzzer. You could try to trace that this variable had type integer, and then you wouldn't try to call a method on it. Other ideas that I want to play with is to maybe generate JavaScript code step by step. So you generate a few lines, and then you run that. And if that doesn't throw an exception, you continue. And if it throws an exception, you go back, and so on. But the approach that I decided to use here is mutation-based. And again, this picture is a bit messed up. I don't really know why, but I guess you can still follow. So with a mutation-based approach, the idea is that in your corpus, which you take your samples from, you always have semantically valid samples in your corpus. And so then for the mutation, you pick a sample, it's valid, you do some small mutations to it, and these small mutations, they have a small chance of making it invalid, right? And so with that, you get a fairly high degree of semantic correctness. And then, depending if you do any kind of guided fuzzing or so, you put samples back into the corpus if they're interesting. But you only do this if the sample doesn't throw an exception. This is really important. So everything in your corpus must not throw runtime exceptions. And then this works. So then the final question, or the final requirement is here, we need mutations for JavaScript code. So mutation-based fuzzer needs some kind of way of mutating inputs. Bit flipping, probably not super effective. Then we run into the syntactic correctness problem. So let's try to figure out sensible mutations to JavaScript code or source code in general. Now, this is also not a new research topic. People are already mutating source code. In my opinion, there's 3 different levels on which you can mutate code. So that's what you see on the right side here. The top level is like the source code itself, the text string. You can flip bits and bytes on there. Probably not very effective. Again, syntactic correctness is a problem. The next level, and this is what people are already implementing and fuzzing with, is the syntax tree, the abstract syntax tree. So it's a tree representation of JavaScript source code. You can change like literals also in it, or you can perform tree mutations, like take this branch here, put it somewhere else, or copy subtrees from another sample, etc. But the observation here is that for the engine itself, the syntactic representation is really irrelevant. It doesn't care. What it cares about is stuff like control and data flow. And so what the engine internally does is it first takes this syntax tree and it converts it to bytecode. And this bytecode is then what captures control and data flow. And so for the same bytecode, there's many different representations in the syntax tree, but the bytecode is the important thing. So what I try to do, I wanted to do something different. What I try to do is to mutate more on a bytecode level, on a lower level. And so things you can do there is you can like mess with instructions, change registers, or you can copy instructions from one sample, put it into the other, and so on. And we'll see some mutations later. So if we want to fuzz or mutate bytecode, we can either pick an existing bytecode or we can make our own. I made my own. I called it FuzzIL just because it sounds cool, I guess. And I guess it's optimized for fuzzing, right? So it's an intermediate language that looks kind of like the bytecode you see, but it's easy to mutate that. And here's an example how it looks like. I guess it's fairly self-explanatory. It has these registers or variables, v0, v1, and so on. And then there's operations. Each instruction has this operation, load int or begin for or binary operation. And they can potentially have these parameters, which is the blue things. So load int here, the first one has the parameter 0, so it's loading the value 0 into v0, I guess. Okay, so that's how it looks like. The important next step here is, of course, this is the JavaScript engine doesn't understand this. So we first have to translate that into JavaScript. So let's talk about that. It's called lifting. Again, this is the same sample on the left side. Let's see how we can turn it into JavaScript. There's multiple ways you can do this. There's a trivial way in which you pretty much convert one instruction into one statement. So these load ints, they become assignments of constants. The begin for starts a for loop, etc. So this is very easy to do. If you want nicer looking code, you can actually also do it. So there's another way to lift this. At the bottom right here, this one uses expression inlining. So you can see it has inline all these constants, 0 and 10 and so on, and like chain together the method calls, etc. But the important idea here is that both of these syntactic representations, they do the exact same thing, right? So for an engine, it doesn't really matter. The bottom right one might be nicer for you to look at, but for an engine, it shouldn't really make a difference. Okay, so that's lifting, but let's talk about mutating, which is the real important part. So here's a simpler FuzzIL program, and I'm going to show a few kind of fundamental mutations for that. So the first one is called input mutator. It's a data flow mutation. It's really simple. It takes an input value of some instruction and replaces that with a different one. So in this case, the call function operation, the second input to that was previously v1, and now it's v0, and now we have changed the data flow of the program. Another mutation here is the operation mutator, which changes these blue parameters. So before that, it would load the global print function, and after that, we made it load the encode URI function and left the rest in place. Then there's the insertion mutator, which is how new code gets inserted into the programs. It generates new code following a bunch of like hundreds or so of predefined code generator functions. In this one, it maybe generates a property load, so there's a load property operation, and it just randomly generates that. And this one has currently the highest probability of producing semantically invalid code, right? It might produce a proper method call on something that's, again, an integer or so. But it still has like a 60 or so % success, chance of success. So it's quite okay. Because it's only doing small changes every time. And then the final one is the splice mutator, I called it that way. What it does, it inserts existing code, and it only inserts parts of existing code. So in this case, it's copying code from the same sample, but of course, normally it takes code from a completely unrelated sample and puts it in the current one. And here it copied one instruction, only the first, but it could also copy 10 or so, depending on, yeah, I guess, randomness. Okay, so here's 4 quite fundamental mutations, and there's a few more that I have. There's one other problem, which is minimization, or one other thing that I'm doing, which is minimization. The problem here that this is solving is that with these mutators, programs can only grow, right? If you insert code, or if you like take code from another program and put it into the current one, it can only grow, and so eventually the programs would get way, way, way too big, like thousands of lines, and then the performance degrades. But the easy solution is to minimize those programs after when they are put into the corpus. And minimization is actually simple, at least the basic algorithm. What you do is you go over the program, you take out like every instruction. After taking out an instruction, you rerun the program, and then you check if the behavior changed. So if you do coverage-guided fuzzing, for example, and you triggered a new edge, then you keep removing all the instructions while still so that the same edge is still being triggered. And for a crash, you do the same thing. So while the program still crashes, you remove all these instructions. So conceptually, it's really simple, but it's quite expensive in terms of executions, right? So if your program has 200 instructions, then minimizing it costs about 200 execs. Okay. Now this talk is also about guided fuzzing. The nice thing is at this point we have a mutation-based fuzzer. So all that's left to do to make it guided is to plug in some kind of feedback system that can say, well, this sample is good, that's interesting, let's keep it. Or this one is maybe not interesting, let's make a new one. What I currently have is edge coverage, more or less exactly what AFL does. Important to note here for the JIT compiler, it only measures coverage in the compiler and not the generated code, which is still pretty useful. So it can still like find code that triggers interesting behavior in the compiler itself. So it does work for JITs. But I guess this is an interesting research question. Can we get like coverage on the JIT code itself or so? And I guess there's also other potentially interesting matrices that could be used. Again, maybe an interesting topic. So then the core basic fuzzer algorithm looks like this. In each iteration, it takes a sample from the corpus, executes it, checks if it got a crash. If yes, then it minimizes the crash and then goes continues. If it did not crash, then it checks if it succeeded. Succeeding meaning it didn't throw an exception. If it did throw an exception, then go back to the next one. But if it didn't throw an exception, then check if it triggered new behavior, new edges, for example. And if it did trigger new behavior, then again, minimize, put it back into the corpus, and then go back. Okay, here's what the architecture looks like. We've seen most of the components now. So the main fuzzer here, or one fuzzer instance, is made up of one corpus and the mutator, the lifter thing, the evaluation, the coverage guidance, and minimization. Yeah, right now there's one instance per target process, which simplifies quite a few things. And then the whole thing or many instances can synchronize over IPC or the network. We'll see this on the next slide. And then, so there's, what I also have is a bunch of optional modules. So the thing is kind of modular. For example, the synchronization, which we'll see next, is one module. It's not necessarily required, but it's optional. Okay, so, and then the main primitive for synchronization is importing. One instance can pretty much send a program to another instance, which will be imported there, and then, yeah, let's see how that works. So, synchronization works in kind of a master-worker scheme, and between a master and a worker, there has to be some kind of communication link, maybe IPC or TCP, sockets, whatever. Then it works roughly like this. This worker here finds an interesting program, says, hey, I found this program, it's maybe interesting for you. So what the master does is it executes it on its own instance, and again checks if it did trigger new edges. Now in this case, it might have triggered new edges, and so then, yeah, it is indeed interesting also for the master, and so that master is going to send it to all its workers, and so the new sample spreads through the global corpus. And the workers do the same thing, they re-execute that sample and check if it's also interesting for them. Yeah, now this is kind of expensive, right? One sample is executed multiple times. There's ways to make it faster. I guess you could just export the bits or the edges that it's triggering also. This sample, this algorithm here is very simple to implement. That's why I have it right now. It has the nice side benefit that non-deterministic samples get kind of filtered. So if the worker triggered a sample that's not deterministic and only triggers this edge 1 out of 100 times, then the sample probably doesn't spread further. So it's a nice side effect, and so I didn't really bother making it better yet. The same happens for crashes, but of course crashes are only sent upstream, right? The crash isn't sent back to the worker or anything, because it's not needed. Okay, so then talking about scaling, this is roughly the architecture that I have running right now. The potential problem is if there's way too many workers for one master, then since the master has to execute all the interesting samples, it might just get completely overloaded. So I have these intermediate masters and then a central one, which collects all the crashes. Synchronization works over a very simple TCP protocol. And the whole thing is really, really easy to set up with, for example, Google Cloud Engine and Docker. You just make a Docker container for one instance, write some scripts to start 100 instances or whatever, synchronize them. Maybe Kubernetes might be a nice thing to try. I heard it's cool. I haven't tried it, but let's see. Yeah, so that's pretty much it. Now I wrote this thing for my master thesis last year, where I had been running it on one server more or less. It did find some stuff back then. But yeah, so currently supported is JavaScript core, SpiderMonkey, and V8, corresponding to WebKit, Firefox, and Chrome. So if you do fuzzing, I guess any kind of JS engine fuzzing, there's tons of assertions and crashes you'll get. So I haven't kept track of them. But you'll see a lot of assertion failures in debug builds. Some of them are interesting, but many are not. You'll see like null pointer derefs. You actually sometimes, or not too, yeah, I guess kind of regularly, you'll find samples that trigger observable misbehavior, where the engine outputs something different, but it's not actually a security problem. And so lots and lots of these. Analysis is also kind of tedious. Some of these assertions, you have to first figure out what's going on to say if that's a security problem. It did find last year 2 CVEs in WebKit and one pretty cool spider monkey register allocation bug. Now it's running on more than one server, so let's see. It did already find some crashes I reported. But yeah, so what is my roadmap for this? Right now I want to do some more cleaning up. Now since I'm at Google, I have to put it into review before open sourcing it. Probably I should also wait for the current set of bugs to get fixed, which I reported in the last weeks. But then I want to open source it. I'm aiming for like in a month or so, but this roughly, let's see. And then afterwards, I have a lot of things on my mind that I want to try. So for example, right now, this thing can't even import existing JavaScript code. It just starts from like one hard-coded sample and keeps mutating that. So probably starting from an existing corpus is a good idea. Let's see. And then the FuzzIL thing doesn't cover all the language features yet. Another thing, I would, as I mentioned briefly, I would like to try this kind of hybrid approach where I generate a sample in multiple steps and see what happens. I definitely need better type tracking, try custom instrumentations, probably. But yeah, so that's already it. So what have we seen? A guided fuzzing approach by mutating a custom intermediate language. Right now, this thing is a fairly, I would say, fairly generic code mutation engine. So probably it would also work for other languages, at least as long as they're dynamically typed. Then it probably works. Watch this space for the open source release. Again, I can't really say when it's going to happen, but hopefully very soon. And I'm definitely looking for collaborators. If anyone is interested in running this, trying this, very, very welcome. Ping me, write me an email or ping me on Twitter if you have any questions, if anything's not working. And with that, thanks for your attention, and I'm open for questions.
Any questions, anyone?
Hey, so this is pretty cool. When doing minimization, have you considered doing any sort of analysis on the IL before trying to minimize it and do something like use step chains so that you can kind of figure out easier what's not being actually affecting the program?
So, not really, no. What I do is I have in the FuzzIL language, there's this restraint that like every variable has to be defined before it's used. So this minimization for some of the instructions that I remove, I can directly say it's important because the output is used somewhere. So that does reduce the number of executions by a lot. But otherwise, it's really dumb. It's really just like removing everything from the bottom up and see if something changes. Yeah.
Thank you for the talk.
Sure.
I think it's very interesting idea and implementation. But can you please go to the slide where you show this one? This one, yes, for last year. So can you please clarify? I mean, you found like more than 50 in one engine and 100, so it's 150 bugs and 3 CVE. But what was the scale of fuzzing? Like how many? Like you fuzzing full 1 year or what? Because it's not
pretty
really
much throughout 1 year on like 8 cores or something like that.
Okay. Yeah.
Yeah, it's pretty hard to tell. Like I was fuzzing it during development, right? So I would like develop something, then start the fuzzer, then see, okay, it doesn't reach as much coverage as before, so probably I should maybe go back.
So you made a modification and
exactly, and then
so
see,
it was
okay,
not clear.
Yeah.
Let's say keep metrics. Okay, thank you.
Sure.
Have you considered, or what do you think about fuzzing the actual bytecode of a specific engine, JIT engine?
So the main problem with that is that the bytecode is assumed to be trusted. So if the bytecode, if you like flip any bits or so, if you increment indices, it's going to crash all over the place because the engine assumes the bytecode is trusted and doesn't do any kind of verification on it. So it wouldn't really, I don't think it would work like naively, just taking bytecode and feed it to the later stage of the engine.
Thank you.
Yeah.
Hello, thank you for your talk. So one of the things that I've been interested in is figuring out how to apply coverage to browsers. You mentioned that you're doing coverage over the JIT engine itself, so you're using something like asandcov or some compiler instrumentation.
Yeah.
One of the things that we did for my class was to convert Tomato into a self-hosted service and then do coverage over the actual types in the grammar tree. So just as, we can talk about this later, but just as a suggestion for anybody working in this space, you know, we have two types of coverage that we're trying to achieve. One is execution and one is data space coverage. And so it may be possible for you to import the BNF grammar that's available through Tomato, which expresses these type relationships in the data that we need to generate, and use that in a way that correlates, I guess, with your ability to do coverage tracking in the JIT engine. But really, I think the efficient search of the object relationships and the properties is an interesting space. You mentioned you were using like a static list of 100 different functions or so to do your injections. So maybe there is a way to enumerate a type tree effectively of the properties and functions that should be operating on each other and efficiently search that in combination with the feedback.
Yeah, thanks. I think we should definitely chat.
Yeah.
I have the coverages right now. It's the easiest thing to implement. It is just fsanitize coverage equals something, PC trace. Right now, I also have it as more or less a workaround for this here. The problem that I don't actually can import any existing code because then through coverage it will find like at least some interesting samples. So it's more of it is to some degree also a workaround for this restriction at this point. But I'm sure there are other matrices and ways to measure, like get feedback that probably produce more interesting results.
All right, so a big round of applause for Samuel.